Okay. So, let me see, because, okay, connected, perfect. And, so let's go back at our picture. Just 1 second. It's better if I switch to the presentation mode. Just 1 second. And while I wait for the presentation to be ready, and yesterday I took your subscriptions for the field trip, May 21st. Is there somebody that didn't? Yeah, please, if you can add your name here. And okay, I need your email and the matricola. Somebody else that needs to subscribe? Very good, thank you. Okay. It's still open, but I think it will be possible to subscribe also next Monday. Next Monday, there is 1 week left. I think it's possible. But in any case, if you know that somebody else would like to subscribe, please tell them to send me an email. And next week I'll give you some details on what we will go to see. And I just would like to remind you that the plan is to come back by about 1:32 p.m. And for the details of the field trip next week, I will tell you everything, some information, and also the meeting point, which will be most probably at Porta Saragozza, which is located on the ring just close by. And I think every one of you knows where it is, but next week we will I'll give more details. Okay, good. And finally, I would like to remind you that we agreed that on Monday we will make a question and answer session at the beginning of the lecture, 15 minutes, maybe also 20 minutes. And the game is that you have to prepare, each of you, if you agree, and I hope that you agree, at least one question for me. And the question can be related to everything is concerned with the sustainability in water resources management, water resources systems. And the more challenging the question is, and the better it is. Meaning that the idea is that we get a kind of a game, and you try to challenge me, and we will see who wins. But you can take the opportunity also to ask questions on what I explained, what I taught during my lectures. Of course, if you cannot be there, no problem. And if you are there on Monday, I would appreciate very much if you could prepare one question. There is no harm, no risk, only possible advantages. Good. One more thing, there will be the survey of your opinions on Monday, May 28th, I think it is. Let me see. Yesterday it was 7, 14, 21, 28. So Monday at May 28th, we will have our last but one lecture and the person who is in charge of it will come at 10:30 to take your opinions. And please, if you can make an effort to be present that day. And before that, I will also tell you what is the purpose of getting your opinion, how the form that you compile is used to assess the career of the professor and to assess the capability of the professor and to distribute the resources to the department and the research group of the professor, etc. But most of all, I'm very keen, I really rely on your critical opinion. So I really would like that you are there that day and you compile the form. So again, May 28 at 10:30. If you are busy, it's just enough if you come at 10:30. I perfectly understand if some of your colleagues decide not to attend, decided not to attend the lectures anymore. But if they attended, at least part of them, please tell them that I'm really keen on getting your critical opinion. And then I will explain you later why. We still have some 20 days, so I have time. Okay, good. And don't forget, if you have any proposal for some interaction, I'm thinking of something to propose to you next Monday after the question and answer session. We still have 2 weeks. It would be nice if you got involved in some more interactivity. And I'm thinking of a web page to be published as part of this ebook that I'm building with these tutorials, and on a subject that is relatively easy to be done, and I'm still thinking of it. I know that you're busy during these days because of preparing exams. I will think of something more to propose to you. Okay, now let's go back, move forward with the design of river barrages. And what we said yesterday was an introduction to the different spillways or weirs. And we talked about the environmental flow spillway, the lowest one in terms of altitude. And then we talked about the main spillway and the diversion spillways. So in order of increasing elevation, we have the environmental flow spillway, the lowest, and then the diversion spillway and the main spillway, which is the highest. And the elevation, again, is decided in order to set priorities for the different flows. The high priority flow is the environmental flow, and it's high priority. And then, after this priority is fulfilled, we go to the diversion spillway, which has the second priority. For the designer and for our customers, is the first priority. But according to our overall context and according to the Italian law, the highest priority is the environmental flow spillway, the lowest. And then the diversion spillway, of course, the diverted flow is our second priority. And then, if the flow in the river exceeds the sum of the environmental flow plus diverted flow, there is an excess flow that we can release as well in the river downstream through the main spillway. This is important to understand because it's very simple if you think at it, but on the other hand I see that sometimes it's not, probably we would need to go and see a real barrage in order to better understand. I see that for students it's not so clear, so I'm spending some more time. Okay, now let's look at the other components of a typical barrage. Once the flow is diverted, we need to clean the diverted flow, to clean from sediments and floating material. Because of course, when you get water from these spillways, you may have some sediments in it. Especially if you take the water during high flows. When there is high flow in the river, there is higher energy. Higher energy means erosion, means bad load, and means suspended material. and we divert the flow, the suspended material is diverted as well. We need to clean the flow from this suspended material. Either floating material, can be vegetables, can be pieces of trees, branches of trees, trunks or stems of trees, can be sediments like gravel, sand. We need to remove them. Why this? Because usually we use facilities for bringing water downstream to the location where we use it. These facilities may be pipes, and then we talk about pressure flow, meaning that water is transported downstream through pressure flow. Why pressure? Why we call it pressure flow? Because water into a pipe is closed, and therefore it gets under pressure because we have water from the river that is diverted, that is placed at a higher elevation, and then we have the pipe that goes down. And at a lower elevation typically, of course, because it's downstream. And therefore you have the pressure of the water in the river that is diverted, that pushes the water into the pipe. The advantage of a pipe is that you can cover high elevation gains. It's not a gain, it's, you can cover high jumps, meaning that with a pipe you can go down very quickly. You cannot go down very quickly in a canal, because otherwise the velocity of the water is too high. If you use a pipe, the advantage is that you can go down very quickly, and also water is protected. On the other hand, if you go down very quickly, you get water under pressure. Water is into the pipe, is pressed by upstream water, and therefore it's under pressure. No problem, but in these facilities, a second option is a canal. If you don't have to cover relevant jumps in terms of elevation, a canal is probably cheaper than a pipe. And in a canal you have open flow. Open flow means that water is at the direct contact with the atmosphere. So it's called open channel flow. The advantage is that usually it's less expensive a canal than a pipe. The disadvantage is that you have to keep a moderate, low slope of the canal. You can't go down very quickly with a canal because, as I said, with the energy of the flow for increasing velocity, you have increasing energy, increased erosion, and also you have increased the risk of overflowing from the canal. You can get overflows from a pipe, you can get overflows from a canal. And, you know, for this reason, the slope of a canal is generally limited, it's very mild. So typically, we use canal as water supply facilities when we don't have to cover big differences in elevation, when the withdrawal is more or less at the same elevation than the delivery. When we have to cover big jumps, big differences in elevation, we use a pipe. In both cases, and this is the essence of what I want to say, in both cases, if you have suspended material, it's a problem. Because if you use a canal, you have reduced velocity in the canal, the suspended material settles down, and the canal gets covered by sediment, filled up by sediment. We have siltation, it gets silted, and therefore after a while you have to clean it. And this is a problem, so we don't want sediments in the water that enters into the canal. If we have a pipe, it's even worse because sediments may erode the pipe, because in the pipe I have a high velocity of water. If I have gravel into it, in the bends especially, we have gravel hitting against the pipe and causing degradation, erosion, failure. So we absolutely don't want anything else than water into a pipe. We even don't want air into a pipe, because if we get air into it at high velocity, there air generates turbulence and again degradation of the pipe. We just want water. Moreover, when we deliver water for irrigation, we can't tolerate suspended material because we may use devices like sprinklers, like other kind of devices which don't tolerate suspended material. So we definitely have to deliver clean water. If we deliver water for civil use, it's needless to say, we cannot have any suspended material. If we use water for producing hydropower, the same applies. The same problem applies. The turbines, if there is sand or gravel into water, gets damaged by these sediments. So we have to remove them. Usually, depending on the type of use that you have to make for water, we have a tolerance. A tolerance that is usually dictated by the builder of the machinery or the producer of the machineries, like the producers of turbines. They state, when they declare the technical behavior of the machine, they also declare what is the max diameter of sediments that is tolerated by the turbine. Usually we speak about diameters of fraction of millimeters, like 0.1 millimeters, 0.2 millimeters. 1 millimeter is already a very potentially damaging diameter. There are types of turbines that are designed in order to tolerate higher dimensions of sediments. The same for irrigation devices. The producer usually states what is tolerated and what's not. The moral of the story is that you have to get an indication from whatever, producer or regulations, law in force. You have to get an indication of the maximum amount of the size of the suspended material that is tolerated downstream for the water use. This is an information that you have to get. How to remove sediments and floating material from the diverted flow? Through the gravel trap and the sand trap. Basically, these are pools. Pools where water slows down. By slowing down, it loses energy, it loses capability to transport sediments, and the sediments settle down. Very simple. They are also called sometimes sedimentation pools. The idea is to divide these pools in a sequence of chambers, because as water is just diverted, you still have some velocity, relevant velocity of the flow, and therefore we slow down the flow gradually. So the idea is that in the first chamber, the velocity of the flow is still significant, and we can remove there only the material with the highest size. So the idea is that in this first chamber, only again the material of highest size is removed. So what is the name of the material of highest size? Typically gravel, so we call it gravel trap. And we isolate this chamber because we try to separate the materials of different sizes. So this is why this first chamber is separated by the second one, and it's separated by a submerged weir. If you look in a cross section, you see something like this. So basically this is our pool, and you have the weirs the diversion weirs here. Let's suppose that you have two weirs, and this is the side wall. So what you see here, this upper line, is the top of this side wall here. So I'm basically making a cross-section along a line that is placed about here. So here are our diversion weirs. They are typically equipped with gates. So these are the gates that now in this position are open. And these gates are generally maneuvered by an engine that is placed here. Let me take a chalk of another color. So this is the device that allows us to maneuver the gate. This is the engine. And we can, through this engine, which is electronically driven, we can close or open the gate in order to close the diversion or to open it. Keep in mind that usually we stop the diversion when the river flow exceeds a given threshold. And why is that? Because when the river flow becomes very high, there is a lot of sediment transported by the current, by the flow, and we don't want to take that very, very dirty water, which is not dirty, it's just loaded by sediment. Okay? Here we have our gravel trap. So this is the gravel trap. And then we have this low crested weir, which is placed here, which is the separation between the gravel trap and the sand trap. And typically the flow here is in this position. So we have the water level, the surface of the water that is placed in this position, and the weir is submerged. And the scope of this weir is to stop the gravel, to keep the gravel into the gravel trap. So we have here, into here, we have our gravel. And of course, periodically, once in a while, we have to clean it. We have to remove this gravel. And the way to clean it is a bottom discharge that is located here, which is normally closed, and it's also indicated here. And it's called flushing sluiceway. A sluiceway is a term that is used to identify a bottom discharge. The difference between a weir or a spillway and a sluiceway is that the sluiceway is usually submerged. When you open it, you have the surface of the flow that completely covers the sluiceway. So the sluiceway works under pressure, at least when it is open. And therefore, by working under pressure, you have a high velocity of the flow through the sluiceway, which high velocity basically has sufficient energy to help cleaning the gravel trap. So basically, with high velocity, the gravel is transported by the flow through the sluiceway. And then at the end of the story, we have to intervene. Once we empty this, we have to intervene manually to fully remove the gravel. Again, the difference between a sluiceway is that it is submerged, while a weir is not. It's the upper part of the surface of the flow. It's a direct contact with the atmosphere. I hope I am clear enough. Did you understand? Okay, the difference between a sluiceway, which is submerged, completely submerged, it's a way out that is completely submerged, while a spillway, also called weir, it's the flow passes over the weir by staying in the upper part at the direct contact with the atmosphere. It's clear? Okay. And then we get into the sand trap. The sand trap usually is longer than the gravel trap. And as an order of magnitude, usually we say that the length of the gravel trap is between 1/3, half of the length of the sand trap. Why the sand trap is longer? It's longer because sand takes more time to settle down, to reach the bottom of this pool. And therefore we want to make it longer, the sand trap, because we want to give more time to the sand in order to settle down. And then the sand trap is sometimes it's divided in two channels, and also the gravel trap may be divided into two channels. And the reason is that if we want to avoid interrupting the flow during cleaning, we need two ways. While we clean one way of the sand trap, then we can use the other one. And of course we need gates here. If we want to isolate one of them, we need to put gates here. Over the weir, over the submerged weir, which separates the gravel trap from the sand trap, we need to put gates. But in some cases it's not divided, it's just one single pool. So it depends on the use of the water, it depends on our needs downstream. The sand trap must be equipped with a bottom flushing sluice way, in the same way because we need to clean it. Also, it's also equipped with a top spillway, which allows us to bring possible excess flow back into the river. So if for some reason we mismanage this structure and we get an excess flow into the sand trap, which is something that we normally want to avoid because we need reduce the flow in the sand trap. We don't want excess water because excess water means turbulence, means disturbances in the sand trap, which reduces the efficiency of the sand trap itself. So if by chance we get excess water, we need a top spillway to make sure that excess water is released back into the river. Okay. At the end of the sand trap, there is another submerged weir, which keeps the sand into the sand trap. And then water flows into what we call an upstream tank. Basically, it's a pool that we make has, in order to fix the starting point of the pipe or canal to the water system. This pool, if we use a pipe to deliver water downstream, is needed, this tank, upstream tank, is needed because we want to make sure that air doesn't get into the pipe. And the reason is what I explained to you before. The presence of air is detrimental, and therefore we want to make sure that the highest point of the pipe is completely covered by water. Let me make a sketch here. This is our upstream tank. Which is divided by the sand trap. Here we have the sand trap. And this is our tank. We want to make sure that the sealing of the pipe is well covered by water. There must be something that we call delta H, coverage, sufficient coverage of the sealing of the pipe. I'm not sure whether in English sealing is a good term for indicating the upper part of a pipe. In Italian we say cielo, which is ceiling, or soffitto, and to indicate as I say, the highest point of a pipe. We say cielo in Italian. I think it is ceiling in English, but I'm not really sure. But I think I conveyed the meaning. Submergence of the pipe. We have to make sure that there is a submergence, a minimum submergence. Okay. Now we have to give some indications to you to design these parts. I think it is, I completed my description of the main behaviors, and the last thing that I would like to say is that downstream the main spillway you need to protect the riverbed from erosion. And the easiest way to protect it is through boulders. You place boulders there in order to avoid erosion downstream. Erosion typically happens during high flows, and it's dangerous because it can undermine the stability of the barrage, so you have to prevent it. There are several options that can be used. This is the easiest one, but of course the diameter of these boulders needs to be designed. We don't insist on this because this is something that is related to structural design, and not really structural because it's a prevention of riverbed erosion, but it's not strictly related with water resources management, so I don't insist on the design of this structure from a structural point of view. But let me instead discuss a little bit how to design these components that I already introduced. And we already know how to design the design flow, how to estimate the design flow through the flow duration curve. Now let me talk about the first issue, which is designing the elevation of the three spillways that I introduced just before. So what is the elevation with respect to the riverbed of the environmental flow spillway? What is the elevation with respect to the riverbed of the diversion spillway? What is the elevation of the main spillway? Okay, we said that the environmental flow spillway is the lowest one. So what is the elevation of this environmental flow spillway? First, it is placed at a higher elevation with respect to the undisturbed riverbed. Why is that? Because we want to create a reservoir upstream. And therefore, typically, what we need to do is to estimate what is the water volume that we want to store upstream the barrage. And the water volume needs to be estimated by ensuring the compensation, typically during the 24 hours of a day, the compensation of the mismatch between water demand and water availability. So, by assuming that your river flow in the river is constant during the day, this is a typical assumption that we make, you have to estimate variability along the day of the water demands. And then with techniques that we don't inspect in detail, we derive a compensation volume. It's intuitive, we can understand easily that if the river flow is constant along the day and the demand is not, we need some storage to compensate this mismatch. We estimate the storage, the needed storage, and basing on a survey of our river, we decide the elevation of the environmental flow speed. This is a rule of thumb. Actually, there are other issues that you need to consider. And other issues which are the geological features of the place, which may suggest that you better design a structure that is not very elevated, because you understand that the stability of the structure depends on its elevation. The higher the structure and the more relevant are the destabilizing forces against it. And therefore you may want to stay on the safe side to give, to accumulate less water upstream in order to reduce the destabilizing forces. Water in premise, which is exerting a relevant pressure on the structure. This means that if you decrease your storage, you may not have sufficient volume to compensate the mismatch in some seasons, typically in the low flow season, but okay. We can afford it. Geological features then, and also